Alright, so today I want to talk about a topic that many people may have seen before, but I want to review it so we're all on the same page. It's going to allow us to do some really cool stuff on assignment 3. And that's complex numbers. So what motivates the complex numbers is if I try to solve this equation, x squared equals -1, it's totally impossible to do that because even if I start with a negative number and I try to square it, a negative times a negative is a positive. So I have to go to a more general number system where I actually also have a number called I. So we introduce this number called I so that I squared is -1. So basically we're saying, okay, in addition to all the real numbers that you're used to, I'm going to allow you to use a number called I, which is the solution of this equation here. So by definition, I squared is -1. And so now I'm in a more general number system where, for example, I can have a mixture of things that involve I and things that don't. So I could have a vector like 3 plus 2i. So it has 3 as its, we say, real component, and it has 2 as its imaginary component. And because we're always going to be able to separate out into coefficients that are purely real, plus a coefficient times I, which we call our imaginary coefficient, we can actually think of these numbers as vectors, as 2D vectors. So what we'll do is we'll plot the real component on the x-axis, and we'll plot the imaginary component on the y-axis. So in this example, my 3 plus 2i, so this is 3 real, so we got 1, 2, 3 here, plus 2i, so this is I, this is 2i. I can actually plot that as this vector here. So this is 3 plus 2i. So just for some more examples, I can also have something like 1 minus I. And that'll be this vector. So I go 1 over in the real, but then I have a -1 as my factor in front of I. So that'll be this vector here. So this is 1 minus I. And I could also have, so if I negate this, then that's just like negating a vector, so that would be -1 plus I, which is this vector. So this is -1 plus I. So whoop-de-doo. So I created a new number system where I can actually think of the numbers as two-dimensional vectors instead of just points on the number line. But what's going to be interesting about this is it gives us a new multiplication rule for vectors. So we've gone over the dot product and we've gone over the cross product, and we even talked about direct multiplication of the components. But this is going to give us something entirely different for 2D vectors. So let's look at complex multiplication. And actually, we're just going to follow our nose here and look at a complex number, a plus bi. So a is the real component, b is the imaginary component. And we're going to multiply that by another complex number, c plus di. And we're just going to FOIL. So we're just going to use the distributive property. So I'll say a times c, so this, the result of this is a times c, plus bi times c, so we'll just say plus bci, plus adi, plus bi times di, right? Now I can simplify this a little bit because remember, I times I is -1 by definition. So I can actually write this term as b times d times -1, or just -bd. So if I combine like terms here and keep the reals with the real and keep the imaginary with the imaginary, then what I get is AC minus BD, that's the real part, plus BC plus AD times I. So this is my multiplication rule. So notice how that's not quite like anything we've seen before. The dot product would just give me A times C in the real, or in the X component, and B times D in the Y component. But here we're actually saying, look, the X component involves A times C, but also minus B times D, and then the Y component is B times C plus AD. So interestingly, both the X component and the Y component involve parts of the X and Y components of the originals. So that's really all there is to it. So it's just, I want you to remember that you can make these things that are complex numbers. You could think of them as vectors, but we have a different multiplication rule. But I also just want to quickly give you some intuition about what this multiplication is doing. So let's say, so actually, I guess I'll give away the punch, well, no, I won't give away the punchline. So I'll say, what is it doing? Question mark. So let's consider some complex number. We'll say x is equal to a plus bi. So we'll leave it open as to what it is. But let's consider another complex number y, so that a squared plus b squared is 1. Or sorry, a complex number y, so that the real component squared plus the imaginary component squared. So we'll say y is equal to c plus di, but c squared plus d squared is 1. So we're just saying y can be thought of as a unit vector. So let me actually just quickly draw y, actually. So we're saying that y is a unit vector. So that's what that means for this, for a square of the real component plus the square of the imaginary component to be 1. And so this is going to be, and another way of saying that is that the magnitude of y is 1, if we're thinking about it as a vector. And if we think of the angle that that vector makes with the origin, what we can say is, well, the x component is cosine of that angle, so the real component is the cosine of that angle. And the imaginary component is the sine of that angle. So let me actually rewrite this complex number y as cosine of theta plus I sine theta. So for any complex number that has magnitude 1, or the square of the real component plus the square of the imaginary component is 1, I can write it in this so-called polar form. And it's just that I can give it an angle and just say that it's going to be cosine of theta plus I sine theta. Now if I look at what is x times y, and I just follow my rules here of multiplication to the left, what I see is that's going to give me, okay, let's just follow it. So a times c, so c is cosine of theta, d is sine of theta. So that'll give me a cosine of theta minus b sine theta plus I, so now we're going to work on our imaginary part. So we'll have, let me do a first. So it'll be a times sine of theta, right? Because that was the d, minus, or no, sorry, plus b times c, which is cosine of theta. Okay, anyway, all I'm doing is just plugging into this formula here. And what I see is, if I multiply this vector a plus bi times the vector cosine of theta plus I sine theta, I get this vector a cosine of theta minus b sine of theta plus I times a sine of theta plus b cosine of theta. Well, if you think about it, this actually should look quite familiar. So if I am going to do a matrix multiplication with a, b in it, then I can then arrange this here and say, well, if I put cosine theta, negative sine theta, in the first row, see that I'll get the real part, right? So I'll say cosine of theta times A minus sine of theta times B. And then if I put these in the second row, so I say the second row is really I sine theta, I cosine of theta. Then you'll see that that gives me the imaginary part. So this matrix should look awfully familiar. If I just forget about the I for a second, then I see that it's cosine theta, negative sine theta, cosine theta. That's a rotation matrix. So this multiplication that we've defined, if we use complex numbers, it rotates my vector x by an angle corresponding to the vector y. And if vector y happens to not be a unit vector, so it's not the case that c plus squared plus d squared is 1, it will still rotate by the angle, but it will also scale the number. So complex numbers act as rotations and scales. And so for that reason, sometimes people call them phasors. They change the phase of things. Okay. So that's what this multiplication operation is doing. But actually, yeah, so once you implement it, you don't even need to really remember the geometric intuition too much. You can just use it. And we'll see that you can do something very cool with it. And we'll do that as our exercise tomorrow.